In this video, we're going to consider the destructive degradation facility that is available in Weibull++. So to create a destructive degradation analysis, we go onto degradation, right-click, add degradation, and then in Weibull++ we have a non-destructive degradation which allows for multiple measurement, and a destructive degradation which allows for one measurement, because after that the sample cannot be used again. So we're going to consider a destructive degradation analysis, but instead of starting a new analysis from scratch, we consider one already been developed. So we have a total of 20 units being tested, and each one has produced just one measurement, after which the unit had to be scrapped. So we have a number of units being tested at 6 weeks with a degradation measurement. We have another number of units tested at 10 weeks with a respective degradation measurement, and the same for 16 weeks and 23 weeks. So we have a total of 20 readings, but grouped into 4 different categories: 6 weeks, 10 weeks, 16 and 23 weeks. Then we have to choose a degradation model, and we can look at sort of literature, or we can rely on a degradation model wizard that will help us to derive the most appropriate degradation model based on this degradation. So we have a linear model, an exponential, power, logarithmic, LOI-LiPo, and we also have a live data model that enables us to characterize how the data changes within each group. So we have a 2-parameter Weibull, exponential, log normal, normal and Gamble. And for that too, we've also got a distribution wizard, but we can obviously rely on our engineering knowledge to apply the most appropriate model. So once we are happy with both the degradation model and the measurement distribution of the live data model, we can then click calculate, and that produces the shape parameter of the live distribution and the parameters of the degradation model. The A and B are the parameters of the degradation model. And we can look at the graphical result. And here we have the degradation. So we have the results at 6 weeks, 10 weeks, 16 weeks and 23 weeks. We also have to set a critical degradation. So in this case, our final reading was 22.31, the highest reading we recorded, and we decided that our critical degradation we reached at 34, whatever the measurement, whatever the unit is. So what we've got on this plot, we have in fact our critical degradation, and we have also the degradation of our units. And once we've done that, we can use the quick calculation pad to interrogate the curve. So you say, for example, we can look at sort of the mean life of our unit if we're interested, or we can look at the probability of failure after, say, a number of weeks, say, for example, 25 or 27, that obviously for which we haven't got any measurement. And so we look at 27 weeks, we got a 2% probability of failure, because obviously we are gradually getting closer to the critical degradation, and we have part of a distribution that will go over the critical degradation. And obviously we can change the critical degradation to represent, say, for example, a variability of our degradation from, say, a single point set at 34 to multiple reading. And that's it.